There's a moment in every civilization's history when someone looks up at the sky and asks a question that changes everything. Not a question born from curiosity, a question born from dread, the kind of question that, once asked, cannot be unasked. That question is not, are we alone? We have been asking that for centuries. The real question, the one science has finally forced us to confront, is this. What happens to us, to our identity, to our entire understanding of existence, when we are no longer alone? Because something extraordinary has happened. The James Webb Space Telescope, a machine so precise it can detect the chemical breath of a world 120 light years away, has done something no instrument in human history has ever done before. It has looked at another world, a real, actual world orbiting a distant star. And it has found something that should not be there, something that on Earth is only made by living things. And the scientific community is not celebrating. They are being very, very careful. That silence, that deliberate restraint, is the most terrifying signal of all. Somewhere in the constellation of Leo, about 120 light years from the pale blue dot we call home, there is a planet, not a hypothetical planet, not a mathematical ghost inferred from ancient starlight, a real planet, photographed, measured, and analyzed by the most powerful space telescope ever constructed. This world is called K2-18b. It was discovered in 2015, and for years it sat in the catalog of known exoplanets as a curiosity, interesting but unproven, promising but distant. Then the James Webb Space Telescope turned its golden eye toward it, and the universe changed. Because what Webb found in the atmosphere of K2-18b was not just chemistry, it was a question so large it threatens to rewrite the story of life itself. But before we get there, we need to understand what it actually means for a telescope to see another world. Because most people imagine this as looking through a window, a sharp, clean photograph of a distant planet hanging in the dark like a marble. The reality is far more complex and far more astonishing. The James Webb Space Telescope does not simply photograph planets, it reads them. It decodes the light that passes through their atmospheres, light from their parent stars, filtered through layers of gas, molecules, and chemical compounds, and it converts that filtered light into a spectrum. That spectrum is a fingerprint. Every molecule in a planet's atmosphere absorbs specific wavelengths of light in specific patterns. And those patterns are as unique as a signature. Carbon dioxide leaves one mark, methane leaves another. Water vapor, sulfur dioxide, ammonia. Each one writes its own name in the language of light. Webb can read all of them simultaneously from a distance of trillions of miles. Think about what that means. We are sitting on Earth, and we are chemically analyzing the air of a world that our fastest spacecraft would take over 100,000 years to reach. That is not science fiction. That is what happened. And when the Webb team analyzed the atmosphere of K2-18b using this method, a technique called transmission spectroscopy, they found carbon dioxide. They found methane. They found traces of water vapor. All of this was extraordinary. All of this was headline news. But none of that is the part that keeps astronomers up at night. The part that changes everything is this. They also found dimethyl sulfide. And if you have never heard that name before, you are about to understand why it matters more than almost any scientific finding in the last century. Dimethyl sulfide, abbreviated as DMS, is a molecule, a simple arrangement of carbon, hydrogen, and sulfur atoms. On Earth, it has one primary source. Not volcanoes, not lightning, not atmospheric chemistry. Life. Specifically, marine life. Primarily microscopic ocean organisms called phytoplankton. These tiny creatures produce dimethyl sulfide as a byproduct of their metabolism, and when they release it into Earth's oceans, it evaporates into the atmosphere, where it contributes to cloud formation and the faint smell of the sea. On our planet, in any significant quantity, DMS means life was here. It is, in the language of astrobiology, a biosignature, a chemical flag planted by biology, visible from space. A team of astronomers led by the University of Cambridge used data from the James Webb Space Telescope to detect the chemical fingerprints of dimethyl sulfide and potentially dimethyl disulfide, known as DMDS, in the atmosphere of K2-18b. On Earth, both molecules are only produced by microbial life, typically marine phytoplankton. And here is the detail that stops every scientist who hears it cold. The team estimates the presence of these molecules to be thousands of times stronger on K2-18b than concentrations of dimethyl sulfide and dimethyl disulfide typically found on Earth. Not equal, not similar. Thousands of times stronger. Whatever is producing the signal, if it is real, it is not a faint whisper, it is a shout. But here is where it gets complicated. Because science does not deal in shouts. Science deals in proof. And the proof, as of right now, is incomplete. The observations reached the 3 sigma level of statistical significance, meaning there is a 0.3% probability they occurred by chance. In everyday terms, that sounds convincing. But the scientific community demands 5 sigma confidence for a discovery to be considered conclusive, a level representing a mere 0.06% probability of random error. 3 sigma is intriguing, 3 sigma is newsworthy, 3 sigma is not a confirmed discovery. Scientists are debating whether the data is really pointing to biosignature gases in the atmosphere of K2-18b. Independent researchers have reanalyzed the same data, some finding the signal consistent with the Cambridge team's results, others arguing the features lie near the noise threshold and could be explained by non-biological chemistry. This is not a failure of science. This is science working exactly as it should. But it means we are standing at the edge of the most important possible discovery in human history, looking into the dark, and we cannot yet be certain of what we see. And this is where everything changes. Because whether or not DMS is definitively confirmed, what the James Webb Space Telescope has already accomplished is revolutionary. The discovery debate over K2-18b is only one chapter in a story that has been rewriting the astronomical textbook page by page, discovery by discovery, since the telescope began its science operations in the summer of 2022. To understand why K2-18b matters so much, you have to understand the machine behind it. You have to understand what the James Webb Space Telescope actually is. It was built over 2 decades and cost $10 billion. It launched on Christmas Day 2021, riding an Ariane 5 rocket into the deep black, folded like an origami miracle. A telescope so large that it had to be compressed to fit inside a rocket fairing, then unfold itself in space over the course of 2 weeks in a series of 344 individual deployment steps, any one of which, if failed, would have ended the mission. The primary mirror is 6.5 meters across, made of 18 hexagonal gold-plated beryllium segments, cooled to minus 233 degrees Celsius, colder than most of the universe, to prevent Webb's own heat from blinding its infrared sensors. It sits at a point in space called L2, 1.5 million kilometers from Earth, perpetually shielded from the sun by a tennis court-sized sunshield made of 5 layers of Captain Foil. It is the most complex scientific instrument humanity has ever placed in space, and it is performing beyond every expectation its engineers set for it. The first evidence of what this machine could do came quickly. The telescope's first released science result, a transmission spectrum of the hot Jupiter WASP-39b showing unambiguous carbon dioxide, marked the beginning of an era in which the atmospheric composition of worlds orbiting other stars could be measured routinely rather than as exceptional feats. Read that again. Routinely. What was once an exceptional feat, detecting a single molecule in the atmosphere of a planet orbiting a star dozens of light years away, has become routine. That is the scale of what Webb has changed. But it did not stop at carbon dioxide. Webb has now characterized the atmospheres of dozens of exoplanets, each one adding a new data point to humanity's growing atlas of alien worlds. Some of what it found was expected. Much of it was not. And a handful of discoveries were so strange, so contrary to existing models, that they have forced scientists to go back to the drawing board entirely. Consider what Webb found when it turned toward a planet called WASP-94ab, a gas giant nearly 700 light-years away in the constellation Microscopium. Astronomers discovered that this planet has a bizarre daily weather cycle, where mineral clouds appear every morning and vanish by nightfall. Every morning on WASP-94ab, clouds made from rocky minerals gather across the sky. Clouds made of rock. Think about that for a moment. On Earth, clouds are water droplets suspended in air. On WASP-94ab, the clouds are made of silicate minerals, the stuff of sand and stone, vaporized by the planet's extreme heat, and then condensed in its cooler upper atmosphere into particles that drift through the sky like a rocky morning fog, only to dissolve again in the heat of the planet's long, brutal day. This finding marked one of the first times scientists have directly observed cloud cycling on a hot Jupiter exoplanet. Not theorized, not modeled, observed. And then there is the story of WASP-121b, a planet that is dying in slow motion, visible to the instruments of Webb in real time. Astronomers have captured the most dramatic view yet of a planet losing its atmosphere, watching the ultra-hot gas giant WASP-121b for an entire orbit with the James Webb Space Telescope. Instead of a single stream of escaping gas, on the planet is wrapped in 2 colossal helium tails, one trailing behind like a comet, the other stretching ahead toward its star. A planet with 2 helium tails, a world being slowly devoured by its own star, hemorrhaging its atmosphere into space, leaving twin streamers of gas that stretch for millions of kilometers across the void. The helium signal remains visible for more than half of the planet's orbit, marking the longest continuous observation of atmospheric escape ever recorded. What Webb is showing us is not merely what planets look like. It is showing us what planets do, how they live, how they die, how they change across timescales we can barely imagine. But as extraordinary as these discoveries are, none of them prepare you for what Webb found when it looked at the nearest significant star system to our own sun, a system called Alpha Centauri, a name you have heard, a system that, at just over 4 light years away, is practically our cosmic neighbor. NASA's James Webb Space Telescope has detected strong evidence for a giant planet orbiting Alpha Centauri A, the nearest sun-like star to Earth, 4 light years away, the closest possible world outside our solar system that could orbit a star similar to our own, a planet we cannot currently reach in any realistic human time frame, but a planet that is suddenly, achingly, intimately close compared to everything else we have discussed. The implications of a planetary system around Alpha Centauri extend far beyond science. They touch something deeper in the human psyche, the ancient, burning need to know whether the universe we inhabit is shared. And that need is precisely what makes K2-18b so seismic. Because K2-18b is not just a planet with an interesting atmosphere. K2-18b is what astronomers call a Hycean world. The name comes from hydrogen and ocean, a theoretical class of planet that is larger than Earth, but potentially covered by a vast global liquid ocean beneath a thick, hydrogen-rich atmosphere. The theory was proposed only a few years ago. When the Cambridge team looked at K2-18b, they found mounting evidence that the theory was correct. The absence of ammonia in K2-18b's atmosphere is part of why many researchers infer that the planet has a vast liquid ocean, their theory being that the ammonia is absorbed by a vast body of water below, an ocean, on a world in the habitable zone of its star, with what appears to be a gas produced exclusively by marine life in its atmosphere. Connect those dots slowly. Let the weight of each connection settle. A Cambridge researcher described the moment in stark terms. This could be the tipping point where suddenly the fundamental question of whether we're alone in the universe is one we're capable of answering. Not answered. Capable of answering. There's a vast difference between those two phrases, and that difference is where science currently lives, suspended between one world and the possibility of another kind of world entirely. But the story does not end with K2-18b. Because while the debate over its biosignatures plays out in journals and conference rooms and on the servers of telescopes still pointed at that distant star, the James Webb Space Telescope has been doing something else entirely, something that, in a different timeline, would be the biggest scientific story of the decade. It has been looking at a family of 7 worlds that may be the most important set of planets ever identified. 7 Earth-sized rocky planets orbiting a single red dwarf star 39 light-years from Earth, the TRAPPIST-1 system. And what Webb found there has complicated everything we thought we understood about habitability. TRAPPIST-1e, the planet most often cited as potentially habitable, showed spectral signatures consistent with a thin atmosphere containing carbon dioxide and traces of water vapor. The absence of a thick hydrogen-helium envelope around a rocky planet at this distance suggests the planet retained a secondary atmosphere formed by volcanic outgassing rather than primordial gas capture. A secondary atmosphere, formed by volcanism, on a rocky planet, in the habitable zone. This is not proof of life, but it is proof of something that science considered improbable just 5 years ago, that small rocky planets close to their red dwarf stars can retain atmospheres at all. Red dwarf stars are violent. They flare. They blast their nearby planets with radiation. The conventional wisdom was that any world orbiting close enough to a red dwarf to be in its habitable zone would be stripped of its atmosphere, sterilized, rendered lifeless. TRAPPIST-1e appears to have survived. And if it survived with an atmosphere containing carbon dioxide and water vapor, then the universe just became an enormously more interesting place. This distinction matters enormously, not just scientifically, but philosophically. Because what Webb is doing, discovery by discovery, is demolishing the idea that Earth is special in any meaningful structural sense. Not in the sense of our value or our consciousness or our civilization, but in the sense of our geology, our chemistry, our atmosphere. Webb keeps finding worlds with water, worlds with carbon, worlds with the molecular raw materials of life. Webb's observations have detected carbon dioxide, water vapor, methane, and sulfur dioxide in various exoplanet atmospheres, providing the first detailed chemical inventory of worlds beyond our solar system, a chemical inventory of alien worlds. We are, for the first time in human history, compiling a recipe book for other planets, and the recipes keep looking familiar. But there is another layer to this story, a layer that the headlines rarely reach. Because while Webb's exoplanet discoveries have captured the public imagination, the telescope's most scientifically disruptive findings have come not from nearby stars, but from the edge of the observable universe, from the very beginning of time. Webb's most disruptive finding remains the existence of massive, well-structured galaxies at distances corresponding to the first few hundred million years after the Big Bang, far larger, more structured, and more luminous than any theoretical model predicted could exist so early. These have been called the impossible galaxies. And impossible is exactly the right word. According to our best models of how the universe formed, models built over decades by thousands of physicists and cosmologists, tested against every observation ever made, galaxies this large should not exist this early. There was not enough time for them to form. Matter had barely begun to coalesce from the primordial plasma of the early universe. Gravity had barely had time to pull gas into the first stars, and yet there they are, ancient, enormous, structured, real. What this means is something that scientists articulate carefully and the public rarely hears in its full weight. Our foundational model of the universe, the model that tells us how everything began, how it evolved, and what it is made of, may be incomplete in ways we do not yet understand. The James Webb Space Telescope, designed to confirm and extend our understanding of the cosmos, has instead revealed that our understanding has holes in it large enough to swallow galaxies. This is not a crisis. In science, being wrong is the path to being right. But it is a humbling, awe-inducing reminder that the universe is under no obligation to conform to human theories. And then there are the smaller revelations, smaller in scale, enormous in implication. Astronomers using the James Webb Space Telescope have, for the first time, directly analyzed the surface of a rocky planet beyond our solar system. The planet LHS 3844b is a so-called super-Earth about 30% larger than our planet and located nearly 50 light-years away. The findings reveal a dark, airless world that may resemble Mercury. An airless rock, dark, barren, hot. Nothing like what we hoped, but everything we needed to know. Because science is not just about finding the good news, it is about finding the truth. And the truth about LHS 3844b, that it has no atmosphere, that its surface is dominated by dark volcanic basalt, that it is silent and sterile and ancient, is as valuable as any discovery of potential life. It tells us what happens when a world loses the conditions for habitability. It tells us what we are looking for when we search for something different. In a discovery published in early 2026, scientists using Webb identified a previously unknown kind of exoplanet, one whose atmosphere defies current ideas about how planets are supposed to form. The planet, PSR J2302 2650b, has a mass comparable to Jupiter, but orbits a rapidly spinning neutron star. Its atmosphere is dominated by helium and carbon rather than the familiar gases seen on most known exoplanets, and it is shrouded in dark, soot-like clouds. Under the intense pressures inside the planet, scientists believe carbon from these clouds could be compressed into diamonds. A planet with diamond rain, orbiting a dead star, with an atmosphere of carbon soot, stretched by gravity into the shape of a lemon. This is a new type of planet atmosphere that nobody has ever seen before, said the study's principal investigator. Nobody has ever seen before. In a catalog of nearly 6,000 known exoplanets, Webb keeps finding things that no existing category can contain. The universe is more creative, more varied, more strange than our models assumed. And this is the deeper truth about what the James Webb Space Telescope is doing. It is not just discovering new things. It is demonstrating, with each new finding, that the range of possible worlds is far wider than we imagined. Every time we thought we understood the boundaries of what a planet could be, how big, how hot, how chemical, how alive, Webb has found something that sits outside those boundaries. A planet with mineral cloud mornings, a planet with helium comet tails, a planet with diamond cores, a planet whose atmosphere may carry the chemical signature of microbial ocean life. The universe does not observe our categories. It does not respect our models. It does not conform to our expectations. And Webb is the instrument that has finally forced us to accept that. Now consider the engineering reality underneath all of this. The James Webb Space Telescope was not just a scientific instrument. It was a declaration, a statement made by the species that built it about what we are willing to sacrifice in the pursuit of knowledge. By April 2026, it has completed nearly 4 years of observations, and its cumulative impact on astronomy is extraordinary. Every month brings new results challenging established models of galaxy formation, atmospheric chemistry on worlds orbiting other stars, and the physical processes sculpting nebulae and star clusters. Every month, not every year, not every decade. Every single month, new data arrives that forces a revision somewhere in the edifice of human knowledge. The telescope that cost a decade of delays, billions over budget, and the careers of thousands of scientists and engineers is now producing results at a pace that exceeds all of its original scientific goals. It was designed for a 10-year mission. It launched with enough fuel, thanks to the precision of its Ariane 5 launch, to operate for 20 years or more. 20 years of data like this, 20 years of impossible galaxies and mineral cloud planets and potential biosignatures. But here's the thing about that word, potential. That single word is doing an enormous amount of work right now in laboratories and offices and seminar rooms around the world. The DMS signal on K2-18b has not been confirmed to 5 sigma. A subsequent NASA-led analysis found the signal at 2.7 sigma. Tantalizing, but not definitive. When it comes to DMS, the new analysis finds a tentative signal that is still well below the 5 sigma level required by the scientific community for a conclusive detection, representing a mere 0.006% probability the data fits the model by chance. Multiple independent teams have reanalyzed the same data and reached different conclusions. Some find evidence consistent with DMS. Others argue the features are indistinguishable from noise or from other non-biological molecules. The full dataset has now been made public, and dozens of research groups around the world are parsing it, building models, running simulations, arguing in journals and preprint servers and late-night email chains about what it means and what it does not mean. This is not confusion. This is the scientific method under maximum pressure. This is what it looks like when humanity stares at the most important possible question and refuses to blink. Because the stakes here are not merely scientific, they are existential. If dimethyl sulfide is confirmed in the atmosphere of K2-18b, if subsequent Webb observations push the confidence above 5 sigma, if the signal survives every independent challenge, then we will know, for the first time with scientific certainty, that life exists beyond Earth. Not a hint, not a probability, not a theory. Life. The knowledge that we are not alone in the universe would not just change science, it would change philosophy, religion, politics, art, culture, language, and the fundamental way every human being on this planet understands their own significance. The Copernican revolution removed Earth from the center of the solar system. The Darwinian revolution connected humanity to the animal kingdom. The Webb revelation, if it comes, would be the third great demotion of human cosmic uniqueness, and simultaneously, paradoxically, the most profound expansion of the human story. Because if life exists on K2-18b, then the universe is not empty. We are not an accident in a void. We are one expression of something the cosmos does, routinely, abundantly, perhaps inevitably. And this is where the story sits right now, on the edge, in the space between 3 sigma and 5 sigma, in the gap between what the data suggests and what the data proves. Webb keeps watching K2-18b. More observations are planned, more analysis is being done. The telescope's instruments are performing flawlessly. The data is getting richer, deeper, more detailed with each new observing run. Webb has increased the ability to detect exoplanets via direct imaging by a factor of 10 times more capable than anything before it. And it is being pointed, right now, at the planets most likely to tell us what we most need to know. Meanwhile, the planet hunting continues on other fronts. For the first time ever, the James Webb Space Telescope discovered an exoplanet through direct imaging, actually capturing a photograph of the world, rather than inferring its existence from indirect signals. The newfound world, TWA-7b, has a mass roughly similar to Saturn and orbits inside the debris disk surrounding a young star. It is the least massive exoplanet ever directly imaged. A photograph, an actual image of another planet, a world orbiting another star, captured in infrared light by a telescope 1.5 million kilometers from Earth. The planet TWA-7b is the lightest exoplanet ever directly imaged, about 10 times lighter than any previously directly imaged exoplanet, showcasing the ability of the Space Telescope's instruments, 10 times lighter. Each milestone Webb passes opens the door to the next, smaller, dimmer, more Earth-like target. And the ultimate target, the one that every astronomer running every program on Webb keeps in the back of their mind, is a rocky, Earth-sized world in the habitable zone of a sun-like star, with an atmosphere that contains oxygen and water and perhaps, impossibly perhaps, life. Expect the Webb telescope will be able to spot planets even smaller than TWA-7b, but directly capturing images of faraway worlds similar to Earth will require even more telescopic power, such as from the extremely large telescope scheduled to come online in Chile in 2028, the Extremely Large Telescope. A ground-based observatory currently under construction in the Atacama Desert, with a primary mirror 39 meters across, nearly 6 times larger than Webb's. When it opens its eye in 2028, it will work in concert with Webb, with ground-based telescopes across the planet, and eventually with Webb's successor, the Habitable Worlds Observatory, currently in early NASA planning for the 2030s and 2040s, to build a picture of the universe's biology that we can barely imagine today. This is the trajectory. This is where we are going. And the direction is toward an answer to the question that every human culture in every era has asked in some form. Are we alone? The question is no longer philosophical. It is no longer theological. It is not even primarily existential anymore. It is technical. It is a question of signal-to-noise ratio, of observing time, of computational power, of the patience to wait for the data to accumulate to the threshold of certainty. We are not asking whether to look. We are not asking whether the answer exists. We are asking when the answer will arrive. And the answer to that question, when, is, for the first time in history, measurable in years, not centuries. What the James Webb Space Telescope has done, what it is doing right now as you read this, is narrow the distance between the question and the answer. It has given us the tools to see what was invisible. It has given us the language to read what was unreadable. It has given us the chemical fingerprints of worlds we will never touch, never walk on, never breathe. And it has made those fingerprints mean something, made them say something about the nature of life, about the reach of chemistry, about the startling, humbling, magnificent fact that the same carbon and hydrogen and sulfur that form the cells of ocean creatures on this planet may also be forming, in some configuration we cannot yet fully name, in the dark waters of a world 120 light years away. K2-18b is still being watched. The data is still accumulating. The debate is still alive. The answer is not here yet, but the telescope is still pointing. The instruments are still recording. The scientists are still analyzing. And somewhere in the data, in the next observing run, in the next reanalysis, in the next paper submitted to the next journal, the number may finally cross the threshold. The confidence may finally reach 5 sigma. And when it does, if it does, the world will never hear the universe the same way again, because the message will have arrived across 120 light years of empty space, from a world we cannot see with our naked eyes, in the chemical grammar of life, and the message will be simple, overwhelming, world-altering. It will say, you are not the only ones. We are living inside the most significant chapter of the most important story humanity has ever tried to tell, the story of whether we are alone. And the James Webb Space Telescope is writing that chapter right now in the language of light, one spectrum at a time. The question is no longer if we will get an answer. The question is whether we are ready for what the answer is.